If you've been creating shaders for some time, chances are high you've often used length or distance functions, which will return the distance from point A to point B. But did you know there are other fascinating distance metrics that can create unique visual effects? Let's see what these distance algorithms are and how you can calculate them. You can call me Digvijay, and now without any further ado, let's get this party started. Let's start with Euclidean distance. The concept was introduced by the Greek mathematician Euclid, which is why it is called Euclidean distance. Let's plot a graph. Imagine that we are sitting at the origin 0, 0, and we have to go to this point P. So the idea is to simply measure the closest distance from the origin to point P. And because the distance will always be a straight line, it is also called as the crow flies distance. And this is basically Pythagoras. Hence, it is also referred to as Pythagorean distance. We can simply calculate the distance d with the square root of x squared plus y squared. But most programming languages already have a built-in function for this, length function, which returns the distance from origin to the point, or distance function, which will return the distance between two specified points. Then there is another distance called Euclidean squared. Let's take our previous scenario once again, and here the idea is, instead of calculating this distance, we will calculate the square of that, which is pure Pythagoras, c squared equals a squared plus b squared. To calculate the distance d, we can simply omit the square root and go x squared plus y squared. Now let's see how this works in the shader. Alright, so I'm on a website called shader.org, which is similar to ShaderToy, but it allows you to write shaders in HLSL. And I was feeling my HLSL is getting rusty, so here I am, just for the practice. Alright, so my UVs are going from 0, 0 up to 1, 1 here. Now the very first thing is I want my UV's origin in the middle. So here I can subtract my half the resolution from the fragment coordinates. So I can simply go minus 0.5 multiply my resolution and then divide resolution.y to compensate for the aspect ratio. So now my UV's y coordinate will go from 0.5 to minus 0.5, but the x coordinate could go beyond that range. Alright, now let me plot my Euclidean squared distance. I'll go float Euclidean squared, and it will take vector 2 as an input, so float 2p. So this function will return the squared length of the p vector from the origin. But if you want the squared length from point A to point B, you can just pass in a minus b when calling this function. Okay, that's easy enough. Then here I'll simply go return x squared plus y squared. Or I can simply go dot product of p and p, and that's basically the same thing that I wrote earlier, so it will do. Then instead of visualizing our UV, let's go length of UV. So this is the Euclidean distance, by the way, and it will give me this nice fading circle. Now instead of Euclidean, let's use our Euclidean squared, and it will just basically darken the values which are less than 0 and brightens the value which are greater than 1. But obviously we cannot see that because the final output will be clamped between 0 and 1. Let's see. And that's our Euclidean squared distance. Next, let's discuss another distance metric known as Manhattan distance. And the idea is, in a city like Manhattan where the streets are laid out as a grid, you cannot simply fly from point A to point B. You have to follow the roads or street blocks. Hence, it is also known as taxicab distance. And the idea is first suggested by the German mathematician Hermann Minkowski. Let's plot a graph, and again, we are at the origin 0, 0. Let's think of the grid lines as roads, and we have destination point P. So to reach here, we can either go horizontal or vertical. Let's say I go 1 unit horizontally, then 1 unit vertically, and currently I've covered 2 units of distance. Then again, let's move horizontal, vertical, and horizontal again to reach the destination P. I've covered total distance of 5 units, which can be calculated by just adding the vector components together, 3 plus 2. Now obviously, the path I've traveled is not the only shortest path. I can travel like this as well, where I go 1 unit horizontally, then 2 units vertically, and 2 units horizontally again. Or I can travel like this, where I go 1 unit vertically, then 3 units horizontally, and then 1 unit vertically once again. But the total distance to travel will always be 5 units. To calculate the distance d, we can simply add x and y components together. However, they can be negative as well, but it would still count as distance, so we will simply use absolute of them. Okay, let's see this in action. Alright, now let me plot my Manhattan distance function. So float Manhattan, and it will again take vector 2 as an input, so float 2p. And here I can simply go return absolute of p dot x plus absolute of p dot y. And I'm dealing with 2D, but this will work in 3D as well. You can simply go plus absolute of p dot z, and it will work just fine. Alright, now let's call our Manhattan distance here instead of Euclidean squared. So Manhattan, and this is our Manhattan distance. Then we have another distance metric, Chebyshev distance, and the idea is given by the Russian mathematician Pafnuty Chebyshev, hence the name. The idea behind Chebyshev distance is how a king moves in chess. It can move in any direction one square, horizontally, vertically, or diagonally. In total, king can move in 8 direction one square. And because the distance is based on chessboard, it is also known as chessboard distance. Shocker. Let's plot the graph, and again, I'm at the origin 0, 0. My destination is point P, and I can move just like a king from chess. So I will move 1 unit diagonally. Now in reality, if we measure the distance, it will be more than 1 unit, but we will consider it 1 unit regardless. Then I can move 1 unit horizontally, and finally I can reach the destination P by moving 1 unit diagonally again. So here I've traveled total of 3 units, which is just the largest component of my vector P. Now again, this is not the only shortest path. I can go like this, where I move 2 units diagonally and 1 unit horizontally. Or I can move like this, where I move 1 unit horizontally and 2 units diagonally. But the distance will always be 3 units. We can calculate the distance d by simply getting the maximum of x and y. Again, they can be negative, so we will use absolute of them. Now let's see this in shader real quick. Alright, so let me create the Chebyshev distance function. So float Chebyshev. It will again take vector 2 as an input, so p. And here I will return maximum between absolute of p dot x and absolute of p dot y. And let's call our Chebyshev distance here. So this is our Chebyshev distance, or chessboard distance. Next we have Minkowski distance, again named after the German mathematician Hermann Minkowski. This distance metric is essentially a generalized version of Euclidean, Manhattan, and Chebyshev distances. It will have an exponent value. Then we will simply use the absolute of our p vector, then go p raised to our exponent value. Then to calculate the distance d, we will add all components together, and then take the entire thing raised to 1 divided by e. Now let's see this in action. Okay, so I will create a function for Minkowski distance. So float Minkowski, and it will take float 2 as input and another float e for exponent value, and here I will go p equals power of absolute of p and e. Then I'll just return t dot x plus t dot y, and then take the entire thing and raise it with 1 divided by e. And let's call Minkowski distance here. So let me pass in the 1. So if I pass in 1, it is Manhattan distance. If I pass in 2, it is Euclidean distance. And if I pass in 3, it moves to Chebyshev distance. Okay, so this is just the generalization between Chebyshev, Manhattan, and Euclidean. All right, now let me animate this. I'll go sine of u time, and this will go from -1 to 1. I want it to go from, let's say, 1 to 4, so I can multiply it with 1.5 and add 2.5. So yeah, it looks something like this. Pretty cool. So next time when you use length or distance function in your shaders, maybe give these ones a try. And let me quickly show you a one real life example. So maybe I can quickly plot a Voronoi noise, and I will go over it a bit faster because this video is not about Voronoi. But still, if you're interested, Martin Steinruckens, aka The Art of Code, has a nice video about it. But still, if you want me to cover Voronoi in details, let me know in the comments below. Alright, so for Voronoi, first I need a function that returns a random vector 2. So I'll go float to random 2, and it will take vector 2 as an input, so seed. And here, let me create a 3 by 3 matrix. M equals float 3 by 3. And here, I will pass in some number and some other number and 0. Then again, I will pass in some number and some other number, 0. Then pass in some bigger number and another bigger number and 1. Then let's go seed equals m multiply float 3 of seed and 1. So here I've just arbitrarily scaled, rotated, and translated the seed vector. Then I will simply go return fraction of seed. So it will return the vector 2 that can go from 0, 0 up to 1, 1. Right now, let me just go like this to make some room here, and here I'll go float Voronoi, and it will take UV as an input and another float for angle offset. Right now here I need grid UV, so I'll go float to grid equals fraction of UV, and I need ID for each grid box. So again, float to ID equals floor of UV. Then I'll go float minimum distance and pass in some bigger value. Then let's create two for loops. So for float x equals -1, x less than equals 1, x plus plus. Then again for the y, I'll go for float y equals -1, y less than equals 1, y plus plus. And this is the same technique we have used in my fence procedural pattern video, so go check that out. Then here I'll first create a vector to offset vector. So offs equals just float2 of x and y. Then I'll go float2 in for normal vector, and I'll just call in my random2 and pass in id plus offset, and just add angle offset on top. Then here I'll calculate the point in my grid box. So id plus float2 of sine of n dot x and cosine of n dot y. And this vector can go from -1 to 1. So let's make it so it only goes from 0 to 1. So multiply by 0.5 plus 0.5. And then let's calculate the distance d equals length of p. And it will only give me the distance or the length of my vector p from the origin, but I want the distance between p and my grid UV, so grid. Then let's check if d is less than minimum distance. If so, we will just update the minimum distance. So min dist equals d, and outside the loop, let's simply return our minimum distance. Let's save, and that compiles. All right, so let's visualize our Voronoi here. So I'll go Voronoi, pass in uv, multiply 4, let's say, and for angle offset, let's pass in 4. And it seems like I messed something up, so all right, let's try mul. But that shouldn't change anything. I changed something, but didn't fix the issue. Yes. Point. Oh yeah, I got it. Instead of ID, you have to go offset. And yep, that's our Voronoi. Now here we are using Euclidean distance, you know. Now let's try to use our other distance matrix. So let's go Euclidean squared, and this will just darken our Voronoi noise overall. Just like that. And if I go Manhattan, it would look something like this. If I go Chebyshev, it would look something like this. But of course, we will use Minkowski, and we will animate it. So sine of u time. Let's go multiply 1.5 and plus 2.5. And that's how you can use different distance matrix in your own shader effects. I hope you found this exploration helpful and inspiring for your shader creation. If you enjoyed the video, please give it a thumbs up. And if you're new here, consider subscribing for more videos like this. And don't forget to hit that notification bell so you never miss an update. If you have any questions or you want to share your own experiences with distance algorithms, write me down in the comments below. I would love to hear from you. That's it from me, and I'll see you in the next one.